Welcome back. We'll be looking at complex numbers today and how we add them. And let's just get to it then. Okay, we have a number here. We have 3 plus 1i, and we have 1 plus 4i. Now the yellow one, the 3 plus 1i, I'm going to let the computer draw it so it doesn't look weird. Remember that the real component, that's what we use this number line for. And there's the 1 right there, also for this red one. Then we have the imaginary component, which goes up what would be the y-axis here. Okay, that's where the imaginary part goes. And I don't really like that they call it imaginary. They should have picked something better because they have real-world applications that go very far and beyond what we can do with just the normal number line. We really need complex numbers, especially in physics. All right, that being said, how do we do this? Well, we're going to be adding the real components, and then we're going to add the imaginary components. And we'll do that this way. This is why I've color-coded it, so you can see what's happening. This 3 is that one right there, and then that's the one from that, because that's the real component and the other real component from the other number, okay? And then we do the imaginary components. So we have 1i. I put it there as 1 because there's a 1 right in front of there. And then there's a 4 right there. That's that 4. Then we have the I just on the outside. So we'll be adding the two things that we have there together. Okay. Now we're going to look at this as though it were just like we used the vectors in physics. So let's go ahead and do that after we've added up the numbers together, because 3 and 1 is 4, and the 1 and 4 is 5. And that gives us together this right there. Okay, so the 3 and the 1, that's this 4. The 1 and that 4, that's the 5 right there. Okay, and it was positive. We had both positives there. If there were some negative numbers in there, we would take that into account too. We don't want to get lost. So this blue vector right there, and the tip of it, of course, is the actual complex number, but we're going to be treating them as vectors. All right, let's take a look at the next one. Just like with the other vectors we've been using, we'll do a parallelogram, and that way you can see how they would add up. So you could either take this yellow one here and then move it up, slide it up so that it's tail to tip, and then you get your finished product there. Or you could have taken this red one and slide it over just like that, following this yellow one there, and then you'd get your other side. But either way, you get a parallelogram, and then you get your nice result, which is this blue one there. Let's look at just the blue one for a second now by itself. And we're going to think to ourselves, okay, sure, we have now a new complex number, but I want to look at this in terms of vectors. So I'm curious also as to how long is this thing? And now we just go back to some simple math that we knew from years ago, and we'll use the Pythagorean theorem, because we know that this particular point right there, there's a base and there's a height, and that means we have a right triangle, and that means we can use Pythagoras with it. So we just a quick little remembrance: if we have a complex number, and we do, okay, that's our number right there, we can find out the length of that by using Pythagoras. Now when we say we have the absolute value of a complex number, that means how long is it from the origin out to the tip of it. Okay, so how long is the arrow that is pointing? And since we have a kind of Cartesian system here, we can just say, okay, we'll do this squared, that squared, add it together, and take the square root. Then we get this, just like we did years ago back in simple algebra. Okay, so it's really no different. And we'll just do what's in front of the number. We'll just use the 5. Although if you did use the I squared, you'd end up with something negative. So we don't want to do that. Okay, we don't want because I times I is -1. So we're only interested in how much of it, because we're interested in the distance, not whether it's pointing up or pointing down. Okay, so, and then we don't want to go take another square root of another negative number when we're already in the complex number plane. We're just looking at how long is it. If you have to walk 10 miles, it doesn't matter to you if you're walking north 10 miles or south 10 miles. It's still 10 miles. All right. Or kilometers if you live in Europe. Okay. So what do we have? We'll take the real component there, square it, the imaginary component, and square it. Okay. Then take the square root of it, then we have it. So let's take a look. That gives us the square root of 41, and you can just leave it like that. There's no point in changing it into something that would be a decimal approximation. I'm fine with it just being radical 41. Okay, so our complex number, the actual solution, because this asked us to add them together, is this here, this blue thing. And of course, it is the tip. It's a place. But we're going to look at them almost exclusively as vectors, which means it has a length too. And shortly, we'll be looking into the angles, and we could already right now use trigonometry to find the angle. We won't do that yet. That's coming up later when we're going to use polar forms. So, all right, so in conclusion, we have the number, which is a point on the plane, and the 4 is positive, so you go over 4, and then you go up 5 on the imaginary part. That's the 5 connected there. And since it is a positive 5 and a positive 4, we know that we're in the first quadrant. Okay, hope that helps. See you next time.